Hi everyone, I'm Jim White, and this video is going to be about thermocouples. There's a lot of misconceptions about how they work, and we'll get into some of the practical aspects of using thermocouples. And then we'll get into a little bit of power generation using the thermoelectric effect. So let's get started. A thermocouple is basically just two wires made of different metals that are connected together. And I want to point out the use of the word connection, not the word junction. Junction has connotations as in semiconductor junction, and a lot of people think the thermocouple effect takes place at the junction. Actually, it takes place near the junction, but I will demonstrate to you that the junction itself doesn't have anything to do with it. So I'm sure I will slip and use the word junction from time to time, but it's really just a connection. Now, different metals generate different voltages along their lengths as a function of a temperature difference. If we have a wire that's hot at one end and cold at the other, a small voltage exists between the ends of the wire. And this is called the Seebeck Effect. And it's rather small. It's typically measured in microvolts per degree C, or reference to absolute 0 degrees Kelvin. Now, the length of the wire does not matter. I can have a very short wire or a long wire. If they're at the same temperature at each end, if this is at the same temperature as this wire, and that the cold end is the same temperature as this cold end, the length of the wire doesn't matter. There'll be the same voltage across the ends of the wires. Now, it's almost impossible to measure the absolute Seebeck effect yourself, and the reason is, here we're representing a wire at some temperature. The instant you stick a probe up against the wire, the end of the probe will go to the same temperature as the wire. So there will be a temperature gradient between the fat part of the probe and the very tip where it's touching the wire. So it appears as though it's a junction, but it really isn't. So it's really the temperature gradient in that area that causes a voltage. Now, there's no Seebeck voltage at superconductor temperatures, and it's very difficult to do, but this is how the absolute Seebeck constants are determined, by cooling one of the conductors to a superconductor temperature. And then you can look at just the voltage at the ends of the other wire. There are many different types of thermocouples, each one suitable to a specific type of application. In the electronics area, generally there are two that are used frequently, the type K Thermocouple and the type J Thermocouple. And I'll talk about their differences. But first, let's look at the physical types. Here is a probe, which is a thermocouple within a metal sheath. If you were going to try to measure the temperature of molten aluminum or something like that, you would need to protect the thermocouple and its insulation from the intense heat. And in the case of a metal probe like this, the insulation material inside is probably a ceramic of some type. Then there's thermocouples that are just basically a wire with the end welded together and a plug-in connector on the other end. You can buy them already made up like this, or you can just buy the wire and the connectors and make your own. Now, both the Type J and the Type K use solderable materials, and this means you can actually solder a thermocouple to something to make sure you have good thermal contact when you're measuring it. Now, here's another example of a purchased thermocouple with the end molded on, and but you can also buy the connectors separately and make up your own thermocouples for your intended purpose. Now, the Type K thermocouple uses a red and yellow color code. And the Type J, which we'll talk about here shortly, uses a red and white color code with a black connector. The Type K uses a yellow connector. Now, you can get thermocouple wire in various gauges, which means the thickness of the wire, and also different types of insulation. The most inexpensive thermocouple wire just has vinyl insulation, and it's only good to maybe 220 degrees C before the insulation will soften. And but as you see here, where the wires are separated, you can remove the insulation for 3 or 4 inches so that you don't have to worry about the insulation itself melting. Now, the insulation on this particular thermocouple is a type of fluorinated plastic, sometimes referred to as Teflon, and it's good to about 500 degrees Fahrenheit. If you're going to go to higher temperatures, you can get it with a fiberglass insulation, and that tends to fray and everything, so it's kind of messy, and you really only want to use it if you have to. Now, the different thicknesses of wire. Here is a Type J made up of number 30 wire, which is roughly 10 thousandths in diameter. And you can get it by the roll. And all this thermocouple wire, by the way, is it's less than $1 a foot. So unless you get into the exotic stuff, it's pretty cheap. And in the electronics area, generally you want to use the fine wire. And you see there's a special connector that has a bobbin on the top that you can wrap your wire around when you're done using the thermocouple. Now here's 3 different meters that can be used for measuring temperature. These two can be switched between a Type J and a Type K thermocouple. And this is actually a multimeter that comes with a type K thermocouple. And there is a temperature setting for measuring the temperature. And all these devices have circuits in them to linearize the output voltage from the thermocouple and make it accurate, maybe within plus or minus a couple degrees. Here's some information on the type J thermocouple. It's useful to 1400 degrees Fahrenheit, assuming the insulation that you pick will handle that. And note that the positive lead is magnetic. That could help you find it if you can't see the colors on the wires. The type K thermocouple is useful to even higher temperatures, 2500 degrees Fahrenheit. And again, the positive wire, which is yellow, is also magnetic. And that can help you find it sometimes. A good place to find information about thermocouples and to purchase thermocouple type products is from omega.com, as well as many other places. Okay, now I've made a rather long connection between the two wires. And if the junction were the important thing, this part out here would be shorting out any voltage generated here. But what is important is that these two different wires are the same temperature as they leave this area. If, for instance, the red wire had better thermal contact than the white wire, I would have an error. So by soldering the connection point or even welding it assures that the electrical contact is right where the wires come together. So that's sort of another proof that it's not the junction. This is just a connection. It's the thermal gradient in these wires that determine the voltage generated and thus the indicated temperature. As you can see on the meter, these temperature has gone up just due to me handling the wires. I had touched the hold button by mistake. So there you can see the thermocouples working just fine, even though the quote junction here is shorted out by the junctions out here. Okay, let's see how we might use thermocouples in an electronics lab. Here's a 5-watt resistor, a 100 ohm 5-watt resistor, and I've used a high temperature silicone rubber that's good for 500 degrees Fahrenheit to 60 degrees C to glue a thermocouple to the body of this resistor. Now that it's set up, I can remove the helping hand here. And then there's another thermocouple that's soldered to the wire lead close to the body of the resistor there. And they're both going to our thermocouple meter. The one on the body is the top one, labeled T1, and the one on the lead is T2. And what we need is 22.4 volts to develop full power of 5 watts. Okay, that's close enough. And we can see the two temperatures taking off here. And when they reach the peak, I'll come back. Okay, it's been about 10 minutes now, and the temperatures are beginning to level off. And here they are in Fahrenheit. Let's see what that is in degrees C. Okay, the body is 160 degrees C, and the lead is 140 degrees C. Now we're in a 72 degree Fahrenheit ambient, the room temperature, which is 22 degrees C. So whatever we're seeing here temperature-wise will be higher at higher temperatures. If you were designing something to work in 110 degrees Fahrenheit, you'd have to add 38 degrees F to the Fahrenheit temperatures. And that's equivalent to a rise of 21 degrees C. So we're on the C scale right now. So if we add 21 degrees to these temperatures, that's what it would be on a hot day if there was no air conditioning. Now, circuit boards, different circuit board materials have different ratings, and a good material has a maximum continuous temperature of 140 degrees C. So you can see you could not run this resistor at full power and have it up against the circuit board, or it will over time it'll char the circuit board. Even the lead temperature is above the circuit board rating, and in a higher ambient it would be even higher. So this is just showing a typical use that you might use thermocouples for. Now on the left here is a power resistor that's rated at 35 watts, but only if it's mounted to a properly sized heatsink. And the part on the right is a 3-terminal voltage regulator. And if you were to use a part like that, you'd have to know how much power you're dissipating in it and know the temperature to see if the heatsink is adequate that it's mounted to. And these are both good applications for thermocouples. And in another video, I'll show you how to measure case temperatures, make your own heat sinks, and size them properly. Well, I had planned to cover thermoelectric power generation as part of this video, but we're getting too long. So I'll cover that subject in the next video. So So I hope you got something out of this one. If you did, subscribe or give us a thumbs up at least.